our speaker. Now it's my pleasure to warmly welcome our distinguished guest speaker for the first session of this program. We are honored to have with us Dr. Alvin S., Assistant Professor at SSN College of Engineering, Chennai, and his academic journey is truly inspiring. He holds a PhD in biomedical device development and MS by research in biosensors, both from the prestigious Indian Institute of Technology, Madras, along with this master degree in medical sociology, medical electronics, and bachelor degree in biomedical engineering. Dr. Alvin's research work stands out for its direct clinical relevance and societal importance. He has developed several innovative point of care diagnostic devices, including system of liver fat assessment, biliary atresia diagnosis, and multiple sample fiber optic biosensing. His collaboration with eminent surgeons and hospitals have enabled him to translate engineering concepts into practical, patient-centered medical technologies. His contribution include more than 10 journals publication, multiple patent, and several device prototypes that have undergone clinical trials. His diverse academic background reflects his deep commitment to both engineering innovations and the impact of healthcare. We warmly welcome you, sir, and look forward to your inspiring session. Over to you, sir.
Thank you, Dr. Gauri, for the nice introduction and the opportunity. And so, shall we start the session? So, today I'm going to talk about the topic from foundation to the advanced concept. Yeah, so this is the simple outline. So I'm going to speak about biosignal generation, how the signal propagate, and electrode-electrolyte interface, different biopotential electrodes, and various types of signals, and how we acquire the signals using electronics. Also, deeply explain about the ECG, and if we have time, we'll touch upon pacemaker also. So, what is bioinstrumentation? So, the bioinstrumentation is the tool of the use of tools and instruments to record and read biological or physiological signals in a way that it can be used for research or in diagnostic purpose. So the among the it's called the term called biometrics. So, what are we measuring in the body? Why should we measure it? What tools let us measure it? How does biomedical instrumentation make those tools possible? Yeah. So for dealing with it, so it's a branch of science that includes measurements of physiological variables and different parameters. So this biomedical instrumentation provides the tools by which the measurements can be achieved. Among those, the first measurement is the range. So the range is the smallest to largest value of a biological or physiological measurement that can be detected or handled accurately. See, for example, if you are weighing machine, so it's range between 0 to 200. So how well it can handle accurately? Yeah. So that's what it is, the range of an instrument. And the second one is the sensitivity. So the sensitivity of an instrument determines how small a variation of or a variable parameter that can be really reliably measured. Yeah, so it can be calculated by the change in output with respect to the change in input. So this is how the sensitivity is calculated. And the third one is the linearity. So linearity says how closely an instrument's output follows in its input. Yeah, and the next one is the history. The hysteresis loop is between the magnetic field strength and the magnetization. Yeah, so the H is the magnetic field strength and N is the magnetization. So when the magnetic field increases, the magnetization follows one path. Where the field decreases, the magnetization follows a different path. Yeah, because two paths doesn't overlap diametrically shows a hysteresis, meaning the output depends on history of its input. Yeah. The next one is the frequency response. So, which is how an instrument sensitivity changes with frequency. Yeah, it must produce original physiologically accurately without any distortion. Yeah. And another thing is the accuracy. So accuracy refers to the degree of conformity between the measurement and the standard, which it can be calculated using the difference between the true value and the measured value divided by the true value. How close to your, of your measurement to its true value? That says the accuracy. Yeah, and the precision. So it's the precision refers to the degree of refinement of measurement that the number of distinguishable alternatives from which the given result is measured. See, for example, if the precision of the value of the device shows around 2.434 or 2.43, so such kind of precision is should be there in an equipment. So it shows how close the repeated measurements to each other. Yeah, that's what the precision of the instrument is. And isolation. The next one is the isolation. Yeah, which is nothing but for any biomedical equipment, isolation should be a necessary one in order to avoid any micro or macro shock. Yeah, so this is used to prevent the interface between the instrument working at the same time from the patient as well as the equipment. There are various types of isolations out there, like magnetic coupling, optical coupling, and also the radio coupling is also, radio telemetry is also there. And another important parameter is the signal to noise ratio. Yeah. So the higher signal to noise ratio means a clearer and more reliable signal you get. And a high signal to noise ratio means the useful signal strength is much stronger than the background noise. So the measurement is cleaner and more accurate. And its unit is dB, is how to calculate it. And the stability. So the stability is the ability of the system to return to its steady state after a small disturbance instead of going into a controlled oscillation. Yeah. So for a good biomedical equipment, the stability also should be more, more important. And the next one is the error. So for any instrument, error is, uh, is always there. So what is an error? It's the difference between true value and the measured value. Yeah, so it's three types. The first one is systematic type, and again, it is divided into three. The first one is the instrumental. So instrumental means the error from faulty or imperfect instrument, like zero error, calibration, or drift error. And the second one is the environmental error. So error caused by surroundings like temperature, humidity, pressure, or any magnetic field, it causes the caused by the environmental error. And the other one is the observational error. So the observational error is error from human reading mistakes such as parallax or any effects. And another type of error is the random error. So the random error is unpredictable variations from noise or uncontrollable factors due to electrical noise, human variation at times, variance, etc. And the final thing is the gross error. So the gross error are the major obvious mistakes made by the operator, which is misreading scales, like reading instrument values incorrectly, wrong data entry type, typing or recording any wrong, incorrect instrument use, like improperly set by the operator. So, and also forgetting about the correction factors, like forget to calibrate. So these are all comes under the gross errors. Yeah. So before going to the next topic, a small distraction. Yeah. So a small question. If anybody knows the answer, you can raise the hands. You have 30 seconds. So which uses more energy? Yeah. So walking muscles, brain during sleep, digestive system, and heart. So the answer is B. So brain during sleep uses more energy compared to others. Yeah. So the next part is biosignal discovery. Luigi Galvani. So he's an Italian physicist and a philosopher. So his assistant accidentally touched a frog exposed sciatic nerve with a charged metal scalpel he was holding, and the leg began to twitch for a second. Yeah. So So this was observed by Luigi Galvani. So this paves the way for this all ECG, GMG foundation. So this is the initial stage in 1791. Yeah. So all it starts from this action potential. So action potential, if you think of it, you have to think this sodium, potassium, calcium, chloride ions, and the hydrogen carbonate are more common like bicarbonate ions. So this is extracellular fluid content and intracellular fluid content. Yeah. So what is action potential? It's a rapid temporary change in a cell electrical membrane potential that allows nerve and muscle cells to send signals. So all this ionic concentration difference inside or outside the cell creates electrical changes that allows the body to generate nerve impulse and muscle activity. Yeah. Let's start with the a resting membrane potential. Let's take a cell. It has extracellular and intracellular uh, ion concentration, as we see earlier. And this has a greater sodium and potassium concentration in the outside compared to the inside. So this is the plasma membrane. It has a phosphobilipid layer, and the cytosol. It has a potassium concentration is more compared to the sodium and other chloride ions. Yeah. Then, because of this difference in concentration, the inside the cell is more negative compared to the outside the cell. Yeah. So, and also it has a different channel like a sodium channel, potassium channel, and also the sodium potassium pump. Yeah, the pump in the sense it uses ATP. Yeah, it uses ATP to push the sodium out of the cell and take the potassium inside the cell. So three sodium goes out and two potassium comes in. So this happens to equalize the uh, cell potential. So what it happens? So if we connect a voltmeter between the cell using a microelectrode, if we take the potential, so it comes around minus 70 millivolts. So that is your resting membrane potential. So anything happens, the small change in the resting membrane potential leads to an action potential. Further, the first one is the threshold. So the threshold uh, is the particular voltage. Above that, the action potential happens. Below that, it won't. The action potential won't happen. So it's called all or none phenomenon. Yeah. So what is happening? So as you see this channel, sodium and potassium channels, the membrane starts depolarization to threshold, which means the calcium channel opens and the sodium enters into the cell. Okay, so by that happening, it is very open, going to very less negative. I mean, it goes to positive, but usually we say it as a very make it very less negative. Yeah, this is the first one. And the second one is the rapid depolarization state. So depolarization means it's a process of making the membrane potential less negative, which means when the sodium channel opens, the sodium enters the cell very strongly. Yeah, so it's called the rapid depolarization state, and it goes to up to 30 millivolt. And the third one is the kind of hyperpolarization or repolarization state. It's a process of bringing the membrane potential back to the resting membrane potential state. Yeah. So what is happening is it's inactivation of the sodium channel. Yeah, and the potassium goes outside. Yeah. So the membrane tries to equilibrate it to become more negative rather than it's positive. So all this sodium and potassium channel. So sodium channel closes, potassium channel opens. Yeah, that's where the repolarization starts. And another one is the hyperpolarization. It's a process of making the membrane potential more negative. Yeah, because the potassium channel is a very slow channel, and not like a sodium channel. Potassium channel is very slow, so it causes more and more negative compared to the resting membrane potential. So in order to equilibrate this, the sodium potassium pump will also be used. And something called overshoot. So the when action so two separate things, one is overshoot and undershoot. So when the action potential becomes positive, it's called overshoot. When the action potential becomes more negative than the resting potential, it is called the undershoot. Yeah. Next, before going to the next topic, we'll see about the a small distraction. So which travels faster? So you have 30 seconds. If anybody knows the answer, you can just tell. Otherwise, I'll give the answer. Yeah, the answer is D. It's the nerve impulse, which is nothing but 120 meter per second. So a nerve impulse travel faster than any other things. Yeah. Then, so this action potential it propagates how? So let's take one example here. We take a neuron, and in the neuron, the action potential first generated the axon hillock. Yeah. So axon hillock is here. Yeah. It's here in this place. So it looks like a hill. So the name term like a axon hillock, and it's propagated down to the axon, axon. So there are two types. What had happened here is the action potential travels along the axon as a result success depolarization and the repolarization of voltage-gated sodium or potassium channels opens and closes, and the action potential travels to the end of this axon. Yeah. So it's of two types. One it's happening in the myelinated and unmyelinated neuron. So in an unmyelinated neuron, which means it doesn't mean that it doesn't have any myelin sheet in the neuron. It has at least one myelin sheet. So it's called an unmyelinated. If it is more than one, it is called myelinated sheet. We'll see in a moment. So the signal moves here is the step-by-step action along the axon. So when one spot opens, its calcium channels let the positive ions in. This charge spreads to the next spot. So this next area reaches threshold fires and triggers the next one. So the action potential travels forward like a wave from one segment at a time. So this is happening in the unmyelinated neuron. However, when it comes to the myelinated neuron, as I said, it has more than one myelin sheet, and these nodes are called nodes of Ranvier, and the process of this action potential propagation is called saltatory condition. So what it happens is this action potential jumps it because this myelinated sheet acts like a insulator. The myelin sheet insulates the axon, preventing ion flow. So the electrical signal is regenerated only at the exposed gaps here, only at the exposed gaps or nodes, we call it as nodes. So at each node, the voltage gated sodium and potassium channel creates a new action potential before it jumps to the next node. Yeah. So before jumping to the next topic, we'll see about the yak chaser illusion. It means you see several purple dots are operating in the circle. So there is something called a green dot. You see sometimes a green dot appears and chases the gap. So such illusion, what does it say? So this illusion, your brain stop noticing the thin background color. It's called proxular fading. Yeah, proxular fading. Yeah, it's called proxular fading. So the missing dot looks like it vanishes. At the same time, your eyes create a green or after image effect, which each purple dot blinks off. So together, this makes a green dot appear and chase around the circle, even though it is really not there. So this illusion is called iliac chaser illusion. Yeah. So let's begin to the next topic, electrolyte interface. So what it is? So you have the previously we have discussed about this action potential, and the action potential happens in each cell. So we want to convert this ionic potential to an electric potential. Yeah. So for that we have to use something called electrode. So this electrode is a type of a transducer. So it converts all this ionic form uh, generated signal into an electric form signal. So for that, we are going to use an electrode. Typically, we use silver clouding. Excuse me, AgAgC electrode. Yeah, silver core electrode. Why we are using it, we will see in the movement. And the electrolyte. So it's a neutral charge. Usually, whatever the metal we are using, that particular metals ions will be also be present in that electrolyte. So in order to sense a signal, a current must flow. Yeah. So the anions in the electrolyte will flow to the. So the anion is the negative, and cation is the positive. M stands for metal, and the electron. So these three helps in creating current flow in the electrolyte interface. What is happening? So the so the anions in the electrolyte will flow to the interface boundary. The cations in the electrolyte will flow away from the interface boundary. To counteract this, the electrons in the electrode will flow away from the interface boundary. Yeah. This create a current in the electrode. This process is called the oxidation of the metal. Yeah. So the oxidation refers to the removal of electron. And, but when comes to the electrolyte, the reduction is happening. Yeah. So why it is most important means there is something called charge double layer and polarization. So in order to measure any biosignal, the electrode should have a non-polarized electrode, which means it should not have a capacitance based. So usually the electrode will be in a, it has an impedance and it has a capacitor. So if there's a charge double layer, it blocks the amount of charge flows through. So it's the polarized electrode. Okay. For measuring any biosignal, we have to use the non-polarized electrode. In terms, for example, for analogy, a non-polarized electrode will be act as a resistor. However, in terms of polarized electrode, it will be like a capacitor. So it stores charges and doesn't allow to flow through. But where do these electrodes will be used? Like for instead of sensing like biosignal, we can use this as a uh, stimulant. See, for example, like cardioverter, defibrillator, or any pacemaker, we have to use an electrode to send the impulse as well as detect the impulse. So for that, any platinum electrodes will be used. So for that purpose, this polarized electrode will be used. For measuring the biosignal, non-polarized electrode will be used. Yeah. So this is the electrode-electrolyte interface. Yeah, and the another thing is you see here. So this is the half cell potential. This is the half cell potential. How it is happening? So there is a charge difference between these two. We call this as a potential. How we measure? We use hydrogen electrode as a standard electrode. We connect between this. So we measure around 0.223 millivolt. So silver electrode has a very low half cell potential, like 0.223, compared to the gold electrode. And these metals have a negative, so we may not use anyway. So usually we use silver electrode since it has a very low half cell potential. And gold and platinum will also be used. However, its voltage is a bit higher, but it is more an inert metal because silver is more toxic. Silver is more toxic, so we may not use in the micro needle or any invasive electrode. Yeah, because because silver ions are a bit toxic. That's why inert metal like a gold will be used in some other application. The next is electrode skin interface. Okay, now previously we have skin, electrode, electrical interface. Now we see about the electrode skin interface. Okay, so for that we take this electrode here and the gel, yeah, the same gel, and we are going to place it on the skin. Skin has a outer layer is epidermis, inner layers dermis and subcutaneous. It also has a sweat glands and all. So I have not drawn here. It also has some sweat glands. It also helps in helps in reducing impedance. And notice nerve endings and capillaries are below the epidermis layer. Yeah. So this epidermis has a high high resistance due to dead skin because it has a more dead skin, and below that the resistance will be much more reduced compared to the below layer. So we see an equivalent circuit here. So here the first one is the half cell potential of this electrode. Yeah, we say usually this one 0.223 volt. Yeah, and another one is CD and RT. Yeah, so the CD and RT we call it as a double layer capacitance and resistance. At the electrode skin boundary ions in the skin and the electron in the metal form. So between this, it acts like a parallel plate capacitor. So separated by a gel. So this is also happening. So this the equivalent circuit of this part. And the next one is the gel. So RS, we call it as the series resistance. So mainly caused by the gel or top layer of the skin. Okay, and the next one is the another half cell. So we usually see this half cell potential, like it represents the half cell potential at the skin electrode junction. Yeah, skin and the electrode junction. In this junction we see a half cell potential. Yeah. Then next one is CE and RE. So it's equivalent resistance capacity present in the parallel. So it's called, E represents the epidermis. Yeah, E represents the epidermis. Yeah, and also it has a leaky impedance from sweat glands and duct. Yeah. So it's called parallel pocket. So it's mentioned in CP RP. So it also has a half cell potential. Yeah, and the final thing is the RE. So it's an underlying tissue resistance, which makes the gel makes it smoother, skin resistance. Sweat keeps because the sweat also has different electrolyte, and so the whole thing behaves like a network of resistor and capacitor that shapes how the bioelectric signal reaches the electrode from here to here. Yeah. So this is the equivalent circuit of the electrode skin interface. Yeah. So before moving to next topic, we'll see about the small distraction. Yeah, it's called the illusion called the cafe wall. Yeah, this pattern uses black and white square that are slightly shifted in each row. You see, it's like you look like it's shifted, even though the lines are not straight. Your eyes seeing them as a slanted or wavy. This happens because your brain tries to join the edges of the squares and get tricked by its contrast. Yeah? So the result is false tilt created by the way our visual system processes lights and dark borders. Yeah. But the same image, if we give color, you see the straight line. So you see the difference. See the difference? Yeah. So this illusion is called cafe wall illusion. So the next, so what are these electrodes applications? There are different types. The first types are external electrodes, subdural electrodes, micro electrodes, and micro sensors. And there are different levels like cellular, tissue, animal, and human level. So among those, this tissue and cellular level, it's called in vitro applications. So in vitro applications means inside the tissue, or if you want to see inside one particular neuron, we call it as a cellular application, we use microsensors or the micro electrodes we use, which uses very fine electrodes inserted into a tissue to record a single neuron or any small regional signals. Yeah. The microsensor is nothing but the tiny probes inserted into tissue or a single cell to measure ions, chemicals, or any metabolic activity present inside a cell. And the next is the in vivo applications. See, for example, if like an external electrode, like to make EEG using any surface electrode. And the next one is subdural electrode. So the external electrode is a non-invasive. It's a non-invasive, and subdural electrodes are invasive electrodes. So this array of electrodes which we placed beneath the skull but above the brain to record any cortical activity with higher accuracy. Yeah, so for that purpose, subdural electrodes are used. And the next one is microelectrode. You know, it's a if you want to measure, it uses very fine electrodes, like needle electrode, inside the tissue to record a single neuron or any small region of the electrical signal. Yeah. So this is also an invasive procedure. Yeah. In microsensor, we cannot use for any human purpose. However, animals, yeah, we should take it for granted. So all this animal study will be there. Just microsensors still in animal study. It's not going for, because all this neural activity will be done using micro sensors. Yeah, it's not done in any human trials due to several ethical okay, so there are commonly used biopotential electrode, and all the figures which I'm going to explain is taken from medical instrumentation JGW book. Yeah. So the first one is your suction cup electrode. It's kind of a temporary electrode used to measure usually the chest leads. We have 6 chest leads will be there while measuring the ECG. For this, suction cup electrodes will be used. And the next one is the metal plate electrode. See, it's a kind of an ancient electrode that still are used. Yeah, it has a larger surface area of this AGCL electrode. And the next one is the metal disc electrode. It's a small disc made of stainless steel or platinum or gold coated disc electrode, usually to measure EMG or EEG. Yes, so, this can be easily integrated in a skull cap or to measure the EEG. Yeah. And another one is the disposable foam pad electrode. Yeah, this we have seen regularly. So it has it's made up of sticky foam. Yeah, middle this is AGCL electrode, and in between this we have electrolyte. This is much more cheaper and easy to use. Yeah. And the next one is the suction cup. It's a type of suction cup electrode, but it's used for fetal ECG electrode. Yeah. So if this is the mother womb or any baby coming out of the uterus, they are going to insert. So this is the coiled kind of a helical in shape like a corkscrew made up of a platinum wire. They simply inserted that into the baby's head or body. It is not used usually, but for any medical reasons, people are using. But nowadays they are not at all using such kind of fetal ECG electrode. Yeah, and another thing is the floating electrodes. The floating electrodes, so it has an electrode here, it's inside here, and this is completely filled with electrolyte, and this is the sticky foam tape. Yeah. So the purpose of this floating electrode is for to measure new moving objects. So if in sports activity, if you want to measure anything, such motion artifacts highly reduced using this floating electrode because it's completely filled with electrolytes. It's a type of floating electrode. And the another one is carbon-filled silicon rubber. So this usually used in babies, newborn babies. where you cannot simply stick other metals like I mean other like a foam pad electrode you cannot simply stick because their skins are very sensitive and if we try to remove those the skin may peel off, so usually they won't use this foam tape, so instead of that one they use this carbon filled silicone rubber and also flexible thin film neometal. These things are used for neonatal ECG applications. Yeah. Then another one is the internal electrodes. So internal electrodes, in the sense, we use usually an insulated needle is made up of stainless steel instead of AgCl. It's made up of stainless steel. It's more, since it's more inert. Because as I already told you, silver silver electrode is really tough. So it's highly used for surface electrodes. But however, when it comes to internal electrodes, they use gold, stainless steel, or any platinum electrodes. Will be platinum or titanium electrodes they will use. So these are all insulated needle electrodes and coaxial needle electrodes. So this is a hypodermic needle. So it is a needle. You see, needle in the middle there will be uh, gold plated or gold electrodes will be there. The outer disk is act as a reference. This act as a reference with a coaxial cable connected to the instrumentation amplifiers. And the next one is bipolar coaxial, which means so this hypodermic needle contains both the positive and return reference electrode will be there. Reference electrode will be there. So this electrode will be used again for any EMG or any inbuilt EMG measurement. So this stainless needle with an insulated shaft or and exposed to for electrical pickup with a lead wire. There's a lead wire fixed at the base. So mainly for EMG to record it. Yeah. And the fine wire needle, this is also an internal electrode. We just puncture the skin using this hypodermic needle. We insert this fine wire, which kind of a J shape. You see, J shape. It's fixed on the tissue. It's fixed on the tissue. Then they remove this needle. They remove this needle. So only the fine wire electrode will be present inside the tissue for high resolution measurement. Yeah. So this inner wire is an active recording surface. And then this is an active electrode. Yeah, active electrode. So maybe outside they keep it as a reference electrode. Yeah. So this will be used, for movement studies or any dynamic EMG. And that is, the thing is, if you see this cross-sectional view, it has two things. So one is like this, this J-shaped, as I told you, the J-shaped. It's anchors in the tissue. Yeah. The other one is the coiled shape. Yeah. It is more, many times it may break if there is a huge movement. However, if it is coiled, it may expand. So based on the different applications they will use. Yeah. So it is used to record deep muscle signals while allowing movement without any braking. That's the purpose of this. And there was metal microelectrodes. So why do we use it? Same. It measures the potential difference across cell membrane. Usually, it's around 0.5 to 10 micrometer here. This one. So it is the outer is made up of glass, inside is made up of metal. So it's called that. That's why it's called a metal electrode. So in order to measure one particular cell, we use such thing. So this solid metal, it's made of a tungsten. It's made up of tungsten microelectrode with the glass supported will be there for extracellular, typically brain or any neurons. Yeah. Then another thing is metal inside glass. That's what we have seen. The next one is glass inside metal. So one put the metal core inside the glass body. The outer The other surrounds a glass core with metal. So both are built this way to make tiny electrodes strong, stable, and able to record signals accurately. Yeah. To in order to record signals accurately, such kind of things might be used. And another one is, metal microelectrode with chip placed inside the cell. Yeah. So so since it is the cell, they are just simply puncturing it with the metal, and these are all insulated one, and the reference electrode will be placed inside or outside or nearby the cell in order to measure one particular cell. So the metal microelectrodes are any sharp and sharp tips that can be pushed directly into the cell to record the electrical activity. And the other one is glass pipette microelectrode. Many times, as you see, these platinum wires have more partial potential, mean more drift will happen. But we want to use the sodium AgCl electrode. But as I told you, the AgCl is highly toxic. So what to do? So what they do have done is so this is kind of a micropipette, glass micropipette, and this is the AgCl electrode will be there, and it's completely filled with electrolyte. Okay, so this metal is not uh, going to cytotoxic this cell. However, we can able to measure the um, cell particular voltage using this glass pipette microelectrode. Yeah. So both do the same job, but glass electrodes are more delicate, and the idea of a precise intercellular recording. So this is what happens, in the metal supported microelectrodes. And electrode array, array means more than one. So it's of the three types, the one dimensional, two and three dimensions are there. So it has a base, a single, so it has a contact pads and different AgCl electrode with insulated leads. It's a single row of electrode placed along the depth. It's placed along the depth. Used to study a layered brain region or any muscle fiber depth. Yeah, in one particular axis. Yeah. So it uses several tiny AgCl. So these are all very tiny AgCl pads and gold conductor. So there were several gold conductors on a thin film probes. Usually around 10 mm cross 0.5 mm cross 125 micrometers. So very small. So many times it's used to measure the heart valve potential. And in an animal surgery, they have used so far, not in the human test, as I already mentioned. And this is the one-dimensional array and a two-dimensional array. So this also has the base silicon base and insulated probes, as well as the AgCl electrode and stuff in a in linear fashion. They used in a two-dimensional array. It's a kind of a flat grid of electrode for surface mapping, used in especially used in EEG or any cortical mapping, muscle activation pattern, or any spatial signal studies. Yeah, such kind of electrodes are used. And finally, the three-dimensional array, same way, it's made up of silicon microfabrication with a comb-like structure. This comb, it's around 1.5 mm of varying diameter. I mean, varying dimension can be used based on the application of the study. It's usually around 1.5 mm insulated tins. So it comes around 1.5 mm, 1.5 mm insulated tins, but only the tips are exposed. Tips are exposed, allowing high density neural and bioelectric signal recording. So for that purpose, this three-dimensional array used. Multiple vertical tins can also be used, excuse me, to capture signals in volume is for deep brain recording, and also it can be used for neural prostheses, brain machine interface, and any high density research in three-dimensional volume or volumetric setting. This type of electrodes are used. And the final is the MEMS technology. MEMS technology. So the first electrode is the beam-led multiple electrode. It has a, silicon substrate. Yeah, and it's made up and above that there is a gold probes. It's an insulated probe, except the tips. Yeah, except the tips, all other parts are insulated. Yeah, silicon dioxide is insulated gold probes. Yeah. This is usually used for a multi-site neural or tissue recording with high spatial resolution. For that purpose, this type of beam-led multiple electrodes are used. Yeah. The next one is multi-electrode silicon probe. Yeah, same way. This also has a silicon base, a silicon probe. Yeah, and the silicon shank has again the bonding pads and the connectors. Yeah, bonding connectors. These bond again going back to connected to any amplifiers, and it also has electrodes. Yeah, same gold coated, gold exposed electrodes. Yeah, this is also ideal for deep brain recording and multi neuron studies. And the final thing is multiple chamber electrode. So it's a cross section of this electrode. It has a different chamber. We'll see one by one. So the first, it also has a gold coated electrode with a chamber and a hole there. Yeah. Why this holes are used? It is useful for localized drug delivery or any simultaneous signal recording, because this tiny isolated chamber had a central hole for controlled chemical or any electrical interaction. Okay, so they deliver a drug to the hole and see the electrical activity of the particular agent. For that, this type of multi-chamber electrodes are used. Yeah. And the final thing is the peripheral nerve electrode. So this is also based with the electron silicon chip, and it contains with different channels and a metal film contact that wrap around or press against any nerve. So yes, these are all different channels. It placed against any nerves, designed for nerve stimulation or any neural prosthetic interface. For that purpose, they. So before going to the next topic, let's have a small distraction. So anybody can answer 30 seconds. So which organ can detect a single quantum event in our body? Yep. The answer is yes, you are correct. Somebody might have guessed. So the answer is retina, because it has rods and cones. So it can detect a single photon, because our eyes is the most sensitive detector in the world. Yeah, compared to any type of photo detector. It gets noise, but our eyes can detect in a single photon. Yeah. Next, so the voltage and frequency range of biopotential. So we have seen the action potential, how the action potential propagates, and how we are going to detect the action potential using electrons. So what's the voltage and frequency range of this biopotential? So everyone know it has an ECG. Yeah. So we categorize using voltage and different frequency. So it has any DC potential in where we will be removing it. And the next is ECG, EEG, EOG, and the EMG will be there. One more thing is missing. Sorry, I missed it. It's ERG, electro. Retinogram is somewhere around 50 to 900 microvolt, and the frequency is around 1 to 100 hertz. It will become ERG. ERG. It will become ERG. Yeah. So these are the particular range of different biosignals from our body. Yeah. ERG will also be there. ERG. And for that, let's touch upon some other biosignals before going to. We'll deeply see ECG in the following slides. Let's see first about the EEG. So these are this is a head, and this is the ear and all. Okay, we connect all this leads with a 10%, 20% distance between the. We are going to place all this scalp electrodes on the ECG to check a different waveform. Yeah. So the first is the delta waveform. It's less than 4 hertz. The second one is theta, 4 to 7 hertz. So this delta and theta show mean sleep or deep thinking. Okay. When we are doing sleep or deep thinking, delta, theta waves here, and alpha 7 to 12 hertz, and beta 12 to 30 hertz. So this alpha shows a relaxed or wakefulness, and the beta shows if we are active thinking or doing any movement. This 12 to 30 hertz will be there. And the final is gamma. I mean, it's a 30 to 50 hertz. It happens when it's a fight or flight event. Yeah. So these relate to high level. So by reading these waveform, EEG help us understand brain states like attention, memory, sleep, and alertness. Yeah. And the next thing is EMG. So this slide shows, EMG signal recording from different forearm, different forearm muscles. While the subject perform a task on a computer, so the each color trace represents each activity of muscle over time. Show how the muscle activate during movement. Yeah, this kind of an EMG signal. And the EGG electrogastrogram. So similar to heart, it has a synusoidal node as a pacemaker, spacer. This also has a pacemaker here in the top of the fundus region, and the signal spreads around it. So it's easy to help in digestion and pushing of food particle to the kidney. So it may not to measure this electrogastrography is used. Yeah. And the electrooculography. Yeah. So it's the to check the eye activity. You see here the movement of eye. Say if we say it's a 30 degree, at 30 degree. Yeah. You see positive increment because it's the eye direction is close to the positive, so it goes to it increases. However, if we see the other direction, like if we connect the potential in the other direction, it goes to the negative potential. Say if it is a 15 degree, so if it is a 15 degree compared to this millimeter, this will be the half. Yeah. So it's a simple EOG recording. Same way ERG, we place some contact lens, electrode contact lens on the kernel surface, and we visually evoke the potential to simulate this retina. Yeah. So that's where the electroretinogram is used. Yeah. So before going to the next topic, we see such type of illusion. You see there's a two straight vertical line placed over the background line that are spread outwards. Yeah. So your brain reads the background as depth. Yeah, is looking down a road with perspective. So to correct this, the brain thinking is a 3D space. So the brain bends the straight line outwards. So this line looked curved even though they are really perfect. Actually, it's a perfect line, but our brain makes it bent. Yeah, so it's a 3D correction thing it's doing. So So the next one is we have seen different types of signal, but how we are acquiring the signal and visualize it. So in order to visualize it, we are going to use different electronic devices. So earlier we used vacuum tubes, then transistor came upon, then ICs, then assembly chips has come. So these are the electronics we are going to use to diagnose or to acquire the weak signal and amplify it and to display the signal. For that, we are going to use an operational amplifier. Uh, to refresh us, since it's a refresh course, we see a simple op amp. Yeah, I see some for one. It has an infinite voltage gain, and the infinite input impedance, zero output impedance. Infinitely, it's fast. Yeah, so this advantages of using operational amplifier instead of any transistor. Yeah, then the first configuration is the buffer amplifier. So the buffer is is a unity gain amplifier. It doesn't have any feedback system inside. So what happened is if we give any input, it gives the same as output, but it will not load your source or any sensor. If we connected this to any electrode to measuring the if it's a hand, if you are measuring this, it will not load the the transistor means the electrode connected here. And the next is the inverting amplifier. So inverting amplifier, we connect the input. This where we connect input, and this is where the feedback resistor. This is usually used to set the gain of the amplifier. So as the name says, it inverts the signal. So if we give a signal as input, the output will be inverted. Output will be inverted. So this as an inverting amplifier. And the next, as you might guess, yeah, it's a non-inverting amplifier. So this is non-inverting means the input given to the non-inverting terminal, which is the positive terminal. Yeah, this. So the gain is also increased compared to the input. Yeah, and but there is no inversion of the signal is happening. Yeah, this gain is set by this feedback resistor. And the next is the differential amplifier. The differential amplifier, I mean, it subtract the given input signal. So if we give any inputs, so, any two inputs, it gives the subtracted output. So this is the circuit. So if we want to have a unity gain differential amplifier, all this resistor like this R1, R2, and this R1, R2 will should be the same. So the unity differential is happening. So, for example, if this 5 volt, this is the 1 volt, the output you will get 4 volt. Yeah. So this is the simple differential amplifier. So how it is happening? The amplifier tries to make this V plus and minus just like a golden rule. It's try to make same. If both the inputs get dropped across this R1 and R2. So the op-amp compares these voltages. So the output keep on adjusting using this, until the feedback path forces the difference V plus minus V plus to appear at the output. So this is how it works, the differential amplifier. Why we are saying this? Yeah, because we are going to use this as in an instrumentation amplifier, all these things. Yeah. So for that we'll see two types of filters. One is high pass and the low pass filter. The using op-amp, we can able to make a high pass filter. With that, we are going to use capacitor in series, yeah, not in parallel. So how this works? This op-amp circuit takes the rate of change of input instead of input itself. The capacitor here, it blocks the or a slow or any steady signal and allows only the fast changing frequency component to pass. I'll give one graphical example. Yeah, so you see here, so it's the fast. So this allows only the fast moving signal. So that's why it's called high pass filter. And the next one is low pass, as you have shared. So only passes the low pass signal. How to design that? It's very simple. We just simply swap this. Swap. So it's between the capacitor will be in the feedback. Yeah, got it. So what is happening? So this low pass are also called as the integrator. So it smoothens and accumulates the input, acting like a low pass filter. So the slow signal passes and fast signal fades away. How this works? This capacitor stores charges over time. So it creates a gradual output change. So the output will be like this. So the fast moving thing will be filtered out, and the slow slow moving signals are passes. So this is how an low pass filter or integrator works. And the next thing is, let's see. So we are going to see about the instrumentation amplifier. We are going to connect any surface electrodes here, left arm, right arm, and left it will be grounded. Yeah, and it is connected to first stage of two matched op amp with the, excuse me, forming a high input impedance differential preamplifier. So ensuring we call this as a buffer stage. We call this as a buffer. These two as a buffer amplifier. You know, so ensuring minimal loading on the body, enabling accurate low-level signal extraction. Yeah. So and then there is a gain resistor. You know, there's a gain resistor. Usually they set it as a 1,000 gain resistor. So the gain of this state is set by the middle or gain resistor following an amplification of this microvolt level ECG by a factor of 1,000 while preserving the signal fidelity. Then we are going to see use the second stage, a classic differential amplifier. Yeah, we are going to use this one. The earlier we have seen, right? So difference between these two output will be given from the differential amplifier. Yeah. So now, if we see another type of thing, we add another op amp which inverts the noise and gives back to the body. It's called ribbon like circuit, which means, see, for example, you have used a noise cancelling headphone. Yeah, the same way this will also be used, where it inverts the noise and gives back to the body so that the noise is greatly reduced. So how we do? We simply average those noise and they give back to the auxiliary op amp. Where see this the noise from these two terminal will be given to this inverting terminal. So it inverts the noise and give back to the right leg. Yeah, this is a right leg. So that's why it's called ribbon light right leg circuit. So how this works? So let's see if we have 1 to 2 millivolt heart signal, and from the right arm and left arm using 0 millivolt signal and 1,000 millivolt noise, 2 millivolt signal and 1,000 millivolt noise, and same it is coming here. So 1,000 millivolt noise, the noise is here, and in addition to this, 1,002 millivolt uh, in the second arm. So the difference with has a 1,000 gain, so you get that 2,000 millivolt in the output. Excuse me, and the noise is getting back to this. So what is happening there? Yeah. So you have a noisy ECG. So this is for illustration purpose, not the exact signal you feel. So from that, the noise will be given to here. Yeah. So it also has a gain of 10,000 millivolt, and the signal, the separate noise will be inverted. So will be inverted and giving back to the body. Yeah. So you may see it's around the 10,000 millivolt. How it will be, because the attenuation will be more the body. So usually we put a gain of 10 to convert this into a huge noise and give. So this driven right leg feedback loop helps in reducing the common mode voltage noise present in the input and feeds an inverted version of back into the patient to the patient leg. So by actively driving the body towards amplifier reference, uh, different right leg loop reduce the common mode interface. It elevates the common mode rejection ratio beyond passive rejection limit. Yeah, this enhances the quality of ECG quality, ECG biosignal quality. Yeah, so you will get a proper clean output signal from the instrumentation amplifier. Yeah. Next, so before going to the next topic, yeah, we'll see a small distraction. So it's called and is a triangle. You know? So you see three black pattern shape are arranged. So your brain fills the actually which is not there. Which is not there. Yeah. So this happens due to the gestalt completion. It's called gestalt completion. So the brain prefers complete the shape over broken one. So you see a bright white triangle that doesn't usually exist. Yeah. Now let's move on to the another thing. So we'll see the detailed about the how an ECG is being recorded using this. So, for example, if you have a chest pain, so what doctor will do? They usually ask to take an ECG. So for measuring ECG, they usually connect different limb electrodes, different four limb electrodes, and six chest electrodes. Yeah, in order to see. So for this limb electrodes usually see the frontal plane, and this chest electrodes to usually see the lateral plane, I mean lateral angle. Yeah. Then it's connected to the ECG machine. Yeah, the ECG machine to check the your ECG. So how this ECG actually happening? So again go back to the action potential. You see the cardiac muscles made up of epicardium, myocardium, and endocardium. You know, endocardium. So if you take one particular cell and we connect an electrode and see between and you measure the voltage between that. If you have I mean, and if it's the heart now is in polarized state, you see both the electrode see, I mean, there is no change in the potential. Both electrodes see only the positive, so there won't be any change in the voltage. But what happens if there is any change in action potential? There is if the positive C is positive, negative C negative, so the voltmeter reads positive reading. Yeah. But what happens in the reverse? Yeah, as you might have guessed, it goes back to the negative volt. Goes back to the negative volt. Yeah. So this is for one particular angle, one particular angle. But what you if you want to see in this direction, what you have to do? Yes, you connect different types of angles. Yeah. So x-axis, y. So different types of angle in the 3D way. You can able to connect. I mean, this will be in this direction. Okay. I can't draw in able to animate this. So I have drawn in this way. So this is how the ECG we are recording. See, for example, so take one particular. I mean, so this is a heart muscle. So this is one type of one electrode. This is one electrode. Consider this is a negative. This is an electrode same as this one. This is positive, same as this one. The yeah the action potential flows from negative to positive. So this negative electrode C is going down. Yeah. However, in the positive it goes up. Yeah. But in between it goes up and down. You see. So this is how it's for one particular thing. We see in the complete session in the next slide. So the same human. So this part is left side and that part is right side. Okay. So many people will confuse this is left arm and this is right, but this is the left and this is the right. So we are going to connect the leads. The color shows is the positive lead, and the blue color is the negative. Please follow it, otherwise you will lose what I'm going to say. So the first lead we are going to be this the lead one. Lead one is the 0 degree. So lead in the sense measuring of different types of angle of the body. I mean we are visualizing the heart electrical activity in different angle. So that's how we are going to measure. So the lead one is connecting between right arm and left arm. Yeah. So this is negative and this is positive. And the lead two is become the positive become negative. So this is negative and this is positive. And the lead three, this is negative and this is positive. Remember, this is as a neutral, right? It's not like this, ground or neutral. Okay, so this is lead 2, and this is lead 3. This is lead 3. So the angle, as I already said, this is 0 degree, and the lead 2 is 60 degree, 60 degree, and the lead 3 is 120 degree. This is 120 degree, so lead 3. And another thing is called, so if we want to measure some other angle, we are going to, so these are all bipolar. Okay. And in order to measure some other angle, we are going to use unipolar electrodes. Okay. See, you see, so our heart is slightly towards the left, slightly towards the left. We may not see which is the middle part. So what we are going to do is we are going to take the lateral angle, like with the different chest leads for to measure this direction. Okay, in this direction. In this direction. Okay, so these are all 6 leads. So total 10 leads in order to measure. So since even though it's a 12 lead system, uh, it says 12 different angle, but we are going to use only the 10 leads. It's not 12 leads we are going to measure. Okay, because 1, 2, 3, 4, and then six leads. So total 10 leads. Yeah, that's it. 10 leads, but 12 different angles we are going to measure. So, and another thing is we are going to take this as a positive, right arm as a positive, and we connect the average of these two connect to this one. Okay, we call this as a AVR. Okay, augmented limb leads. We call it as augmented unipolar limb leads. Why? Because it measures the angle of negative 150 degrees Celsius, negative 150 degrees Celsius, or uh, positive 210 degrees Celsius, whatever it is. Both are same. The next thing will be shifted like this. Okay, this is positive, and the other two will be negative. So we call it as small a, capital B, L. So augmented unipolar left arm. Okay, left arm. So it shows minus 30 degrees Celsius, sorry, minus 30 degree angle. Okay, it measures upward. Then another final thing is foot. So this is positive, and the average of the other two will be negative. So since it is straight, take 90 degree. Okay, this AVF, okay, AVF is straight downwards, and it measures the 90-degree angle from the heart. Yeah. And these are all the different lead configuration and different angles which we are okay. Now you can see. So this is AVR, AVL, lead 1, lead 2, AVF, and lead. Okay. So all these angles are covered in addition to this chest leads. Okay. So what is happening there? If we see in the as a vector diagram, there's a relationship between the two leads. Like A2 and A1. If you see that this is the cardiac vector, using this, using this into triangle, we see a cardiac vector over here. So this vector is drawn here. What it says usually is the component of M, this vector in the direction of A1. So this also, and this A1 is also in the same direction. So the dot product of these two vector is denoted here. Yeah. So you see, we project this here. Okay. We project this here. So this is denoted by around yeah, A1. So this lead A2, it is actually perpendicular to this vector. So there is no voltage components has been seen uh, in the lead. Okay, so only the both, if both are in the same direction, you can able to see some voltage in the leads. Okay, some voltage in the lead. That's what happened there. So for this cardiac vector, usually we see action potential like this, like negative, overshoot, undershoot. But when it comes to cardiac action potential, it's completely different. You see here, there is also a resting membrane potential below minus 80 millivolt. Yeah, and there is something called threshold. There is a threshold potential above that. The action potential may not happen. Yeah, so if it crosses the threshold, what happens? It's overshoot. Yeah, it's overshoot. So the action potential, upstroke action potential happen. Yeah, so this is called phase zero or rapid depolarization. What happens here? So the sodium channels open. I mean, as I already told you, the sodium channels are fast compared to the potassium or any calcium channels. So the fast sodium channel opens, so sharp influx of sodium gets into the cardiac cell. And then slow calcium channels also begin to open, but it will contribute later. Okay. Now the phase two, the second one is phase two. Sorry, that is phase zero. This one is phase one. So the phase one, we call it as an early repolarization state. What happens here is this fast calcium channel happens during the sample potential. It closes. Yeah, fast sodium channel closes rapidly. So the initial brief output of movement of potassium channel begins the repolarization state. But, but not like a simple action potential, there is something called the phase two, which is nothing but a plateau state. Okay, so this is called the plateau state. What happens here is the calcium inflow continuously slowly into the via calcium channel. So there is a something called the L-type calcium channel will be there. L-type cancer will be there, which approaches the potassium efflux. So it balances the membrane potential and makes us a plateau. So the calcium enters from extracellular cellular fluid and the sarcoplasmic reticulum, enabling the contraction of the heart. Yeah, that's what happening during this period. And the next one is the phase three, which is nothing but the final repolarization state. So what happens here is the calcium channel closes. So the L-type calcium channel closes and the potassium efflux increases greatly, which returns the membrane towards more negative. Yeah, towards more negative. So the sodium potassium distribution gradually restored by the sodium potassium pump. As you remember earlier, yeah, sodium potassium pump will be there. So three sodium it's going out, two potassium comes in. So the sodium potassium pumps maintains the equilibrium. And the final state is the diastolic depolarization, which is nothing but the comes back to the phase four is resting membrane potential. What happens here is the potassium leak channel maintain the resting potential, which is nothing but the minus 19 millivolt, minus 90 millivolt, yeah, because the membrane is highly permeable, impermeable to sodium. So what happens here is the from phase zero to phase three. So this period is called long absolute refractory period. That is the refractory period. No matter whatever the extra stimulus we are giving, the action potential will not stop. So this protects the heart from tetanus. So this protects any shock. Tetanus is shock. This protects the heart from tetanus. Called alternative. Yeah. It ensures the rhythmic beating rather than any sustained heart. That's what's happening there. Yeah. Then we will see how we know about the ECG waveform like PEQ or ST. What is happening? How it is happening? Actually, one by one. Yeah. So this is the heart. Yeah. These are all the different currents there inside and SI node. Venous currents are there, hospital fibers and currents are there, arterial muscles and currents are there, ventricular muscles and currents are there. So there are several currents are there, but how it is happening? Let's see one by one. Okay, so what's happening here? The heart is beating. The initial pacemaker is from SI node. Yeah, the SI node is where the natural pacemaker is happening. It's above the atrium. Yeah, right atrium. Now, what is happening? So if we want to measure, see what type of lead it is. If we measure 60-degree, so it is nothing but the lead to. Okay. So we are going to measure lead to how the ECG waveforms are generating. So initially, the heart is in polarized state. Completely, it's shown in the plus. So for time being, we are going to see very few and how this action potential propagates in the heart and how the ECG waveform is generated. Yeah. So the first what happens here, the once the SI node depolarizes, it depolarizes complete atrium, both and left and right atrium. Yeah. So if you want to project this initial state, uh, there's no voltage. Yeah. Next, the action potential propagates from SA node to AV node. What is happening there? The positive becomes negative, and you see here. Yeah? You will see because the positive, then the positive C is positive, negative C is negative, so there is a potential. Consider it's a battery. Consider it's a battery. So you see a positive increase in the velocity. Okay. Now, then it's go back. So then it goes back. So this wave is called P wave. Yeah. So you know about the as I already mentioned, the storing channel opens potential channel. So that's what it is happening. Then the second is SA node. It goes back to the AV node. AV node also has many Purkinje fibers. Many Purkinje fibers. Yeah, here, many Purkinje fibers, but it will be like this. So this the heavy node is like this. Okay, so there is a small change in anatomy. So the uh, the action potential moves from right to left. So as I pointed out this arrow, it will be in this direction. So the depolarization happening, and if we project this, you see there is a this is the Q wave. Okay, it's happening. So this is happening to this is the Q wave. Okay, because since it is the negative electrode C is positive, negative, yeah, positive C, negative. Okay, this is what that's why the Q wave is coming in this direction. Okay. Now, due to the presence of Purkinje fiber, the complete ventricle is depolarizing. Yeah, in a quicker fashion. Okay, when compared to the atrium. Atrium doesn't have any Purkinje fiber. Okay, doesn't have any Purkinje fiber. That's why it takes more time to depolarize. However, since the AV node has ventricle has Purkinje fiber, it depolarizes quickly. Okay, so if we project that, yeah, that is the R wave. Okay, it's the R wave. Now, what is happening here is there is a small portion still not depolarized yet. Okay, uh, because since it is slightly in this direction, depolarizes first, and then secondly, this part is depolarizes. So once it depolarizes, again it comes back since the both are in the reverse, the battery is reverse, so it goes back to yes. So this is the yes. So since it is more fast, the QRS complex is very fast compared to the P wave. If you have written it to some P wave. Okay. So this is the QRS complex. Now what is happening here is the atrium is already depolarized, but it has to be repolarized. Okay. So what happens here? Again, there is a repolarization begins like this. So let me erase this one. Okay. Okay. So it is in the opposite polarity. Because since it's repolarizes, the atrium repolarize, you see the inverted T wave. So this is an inverted T wave. Uh, due to the presence in atrium. But the problem is we may not see that in actual ECG. Why? Because the QRS complex uh, uh, is more. This T wave is obscured by this QRS complex. Okay, so this will not be seen elsewhere in the ECG waveform. And next is the ventricle repolarization state. So, as you can see, we previously we have seen the depolarization happen in this direction. Okay, let me change the. Okay, so depolarization earlier happens in this direction, but the ventricle is in the very high pressure. So all this tissue present here is obstructed, and that's why it is not repolarizing from inside, from epicardium to endocardium. Rather than it's this contraction happens in this direction. Okay, from outside to inside. So that's where the heart pushes the blood outside the left ventricle, from both the ventricle. Okay, so this again, if we project this, we get to see T wave. Okay, see T wave. Okay, now everything goes back to the resting potential. This is how a simple ECG is formed. Both are depolarization and closing and opening of these channels. Yeah, and then so let's have finally instruction. So the body. So if anybody know the answer, you have 30 seconds to. So the body's most electric organ. Yeah, you're correct. So it's the EMG. So the EMG amplitude it just instantly goes. Okay, then the final. I believe we have some time. Okay, I think we have some time. Okay, I'll cut short this. A simple pacemaker. When compared to, so those ECG and all via hearing signal, but here we acquire signal and also deliver an artificial signal using this pacemaker. If the sinusoidal mode is not functioning properly, we are going to give some this potential to beat the heart. Okay. Further, there's a simple pulse generator they use electrode. So for this, you remember we don't use AGCL electrode. Yeah. Instead, we use platinum electrode. Yeah. Okay. So these are the things will be used like thing. So there are simple SA node failure. Yeah. So if we had time, maybe in next session we'll see. Okay. So I think have done. So if you have any questions, feel free to ask. And thank you. Yeah, you have some question? Am I audible?
Yes, sir. Yes, sir. Participants, any queries?
If you can unmute,
If
you
it
can
is,
ask question. Otherwise, you
yeah,
can. Uh, otherwise, uh, you can use my email to communicate. I'll definitely reply to your email. Thank you very much. Thank you, Dr. Gauri, for this opportunity to present. I
thank you. Thank you, sir. Your session has not only expanded our technical knowledge but also inspired us to think critically explore new directions, and appreciate the profound impact of biomedical engineering on society. Thank you once again, sir, for your valuable time, your dedication to knowledge sharing, and your contribution to the success of today's program. We look forward to many more opportunities to learn from you in the future, sir. Thank you, sir.
Thank you.
Thank you. Thank you. Sir. Dear participants, kindly register your feedback, which you should open from your registered mail ID. So kindly make it fast. The link will
Hello,
be
ma'am.
closed as.
Actually, we can't open that link. It is not
Yeah,
opening.
open with your registered mail ID, ma'am.
Uh, it is not able to open, ma'am. So everyone is telling the same only. It is not in that format.
Yeah, but we have received more than 30 plus responses, ma'am.
Maybe you can repost it.
Yeah, okay, sir.
Hello.
Yes, sir.
Actually, I was about to ask some doubts. I raised my hand also, but I was not replied. I don't know how to. Would it be better if if I send the doubts in the short message?
No issue, sir. Kindly send it to SAR mail ID.
Okay, okay, okay.
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 Participants, I have posted the feedback link again, so kindly go through it. So the next session will start around 11:15. So within that, kindly fill up the feedback forms.